Hello, my name is Ehsan Masoudi. I'm from Iran, but I'm studying in Germany, and I'm doing my PhD there. So I'm going today to talk about optimal design for nonlinear models and my package. So at first, I have some preliminaries, but there are not a lot. I cannot explain it in 15 minutes, and also a little bit about imperialist competitive algorithm, and then my R package, ICAOD, or imperialist competitive algorithm for optimal design. And suppose we have a nonlinear regression, and we are in the step of data collection. So in the previous talks, they all have some kind of data, but we don't have a data. We want to tell the experimenter how to choose the data. So suppose, for example, in a medicine study or in the pharmaceutical studies, we can control the dose drug, and then the dose of the drug, and then we want to say which optimal dose we should use. So if I go back again, so I should know the how many optimal level of the independent variable can I have, and what is the optimal value of each level, and then how many optimal replicate per each level. So in optimal design, we just formulate these questions as approximate design, which is this is the design points, and these are the design weight, and it is a probability measure. So its sum should be to 1, and then we are looking for K, Xi, and Wi's, and also with this constraint with this equality constraint. And then we have a kind of general equivalence theorem that can be applied to verify the optimality of the generated design. And because for nonlinear model, this is the information matrix. So if I go back again, so this is the information matrix, the Fisher information matrix. We know that the inverse of the Fisher information matrix is asymptotically equal to variance-covariance matrix. And in the estimation, we want to have the minimum variance for the parameters, for example, for the logistic model. So we choose the Fisher information matrix in optimal design. And then because for nonlinear model, it depends on the unknown parameters, which are like here. This is the unknown parameter. This is the unknown parameter, unknown parameters. And so we should remove this dependency somehow in the Fisher information matrix. In locally optimal design approach, we do that by choosing some initial values. For minimax optimal design, we just maximize over the parameter space. Unfortunately, this function is not convex or concave, so we are completely in a continuous search space. And this is the standardized maximum D optimal design, which is here. We use a locally optimal design here again from up. And then we have a Bayesian optimal design that we average out the unknown parameter. And I prefer to look at optimal design as an optimization problem. So I would like to use I have used the imperialist competitive algorithm. It is completely new, 2007. It is introduced by some people in University of Tehran. Unfortunately, this person has died, and Lucas was died in 2010 because of the cancer. And for more information about the algorithms and how I applied that in optimal design, you can look at my paper here. And I cannot explain it more because we don't have much time here. And so I go straight to my package. So in CRAN, there are some package for optimal design, but most of them, they are about linear model. And in linear model, we don't have dependency on the parameters. So when you apply, this kind of functions, you will get the answer like in fraction of seconds. But for nonlinear models, we should remove the dependency on the parameter. So there were no packages. And there are, for example, also in SAS, I think it's something available, but I'm not sure about that, but I know about JAMP, if I pronounce it true. So they have kind of such things, but the problem that when they repeat the results are not consistent because they use kind of quadrature methods, and it depends on the randomness. But here I try to, I wanted to be consistent with the result. And I use this algorithm here, the optimization algorithm. We cannot use most of the optimization algorithm in R because when they want to correct the out-of-bounds values, they go on the bounds. and it doesn't mean, it doesn't make sense for the weights to go on the bond. For example, I have 4 weights on the bond, or on the other hand, it may produce singular designs. Like, for example, I'm looking for a 2-point design, but when I go on the bonds, practically I will have 1-point design, which is not good in optimal design. Because of that, if you use optim function, you will get not a number produced, or you will get error probably. So this is the package, and the core function here is Mika, minimax ICA, and this is the lower bound of the design space, upper bound of the design space. For example, the dose level, it can be from 0 milligram to 100 milligram, and you only need to specify the Fisher information matrix. It can be as a character or as a function, because I have some functions, default functions in RCPP, which is very fast, better than just defining the function by user in R. And this is the lower bound of the parameter, the upper bound of the parameters, the maximum number of iteration, the number of design point. Usually we start with, for example, the minimal number of support point, and then we increase it by 1, and then we check the general equivalence theorem to see which one is the optimal one. And I also have here a type of optimal design. It can be locally minimax standardized, and I'm working on the Bayesian optimal design as well. And you can have also initial values like every optimization algorithm. And this is for locally, the function that if you want to use the standardized version, you should also specify a function here which gives you a locally optimal design, numerical, analytical solution. And so these are the description of the arguments again. I also have some tuning parameters, which some of them are for the optimization algorithm itself, and some of them comes because of the design problem. So the most important tuning parameters here are the number of countries, and also the inner, for the maximum over the parameter. So I will have this parameter as well, which goes to the NLOPTR direct L to find the maximum over the parameter. So maybe I should a little bit explain about the imperialist competitive algorithm. So in this algorithm, we have kind of number of countries which are equal to the, for example, particle in particle swarm optimization, and we have, for example, some imperialists and we have some colonies, and the imperialists kind of leading the search, and the colonies, they are following the imperialists with some randomness. And then there are also some, for example, competition between the imperialist, the more powerful imperialist, it takes possession of the weaker of the colonies of the weaker imperialist. And then when an imperialist, it doesn't have any colonies, then it will collapse. So it is kind of in real world, for example, in the past US and Soviet, so they have some countries which together, and they, for example, US tried to improve some countries like in South Korea, Japan, for example, they become more industrial, and they reach to the better position to just approach the, for example, economical situation or democracy situation or political situation in US. And for example, on the other hand, the Soviet, for example, the imperialist is kind of, the empire is kind of collapsed. And nowadays, we also have some kind of this hidden imperialism in the world in this model. And so let's go back to the model. So we have here, for example, a 2-parameter logistic model. We use it a lot in, for example, pharmaceutical studies, and also in item response theory in psychology department. So it is a difficulty parameter here, A. And X is a latent variable, which we cannot observe, but we suppose we can observe that in optimal design. And also there is a discrimination parameter. And this is the design interval, and this is the initial value for the parameter. So I suppose from the previous study that the parameter may be around these points, and then I use this function, like I will give here a logistic regression here, a pre-default function here, and then I will have this result in like less than 1 second. So it is a 2-point design, the parameter, the best criterion value, the log determinant of the Fisher information matrix, and I will explain that one now, maximum of derivative plots and the efficiency lower bound. And these are the low-cost search. I just added the low-cost search to the optimization algorithm because, in optimal design, when we do optimization, we need also exploitation because we get near to the optimal design, but we still need to process the algorithm. And local search help us to not have premature convergence. And this is the algorithm, so you can see that after maybe 12 or 15 iteration, it will converge, but this is the area that exploitation is happening by local search. And here is the area that is happening by assimilation, moving toward the imperialist. And so this is the derivative plot. This is based on general equivalence theorem. In approximate design, we always can have this plot, or usually can have this plot. So, how to compute the efficiency lower bound? I just, again, optimize this function, or maximize this function, and found the maximum here, and then the parameter, the number of parameter divided by number of parameter plus this one is the lower efficiency bound based on Atwood. So again, in plotting this function and in checking the optimality of the design, I should do another optimization. So you can see how many levels of optimization I have here. So it makes kind of, tuning parameter to be a lot, but I try to just reduce them as much as I can. And this is the second question. This is for minimax optimal design. So instead of a kind of initial value for the parameter, I have a bounds for the parameter. So it is between 0 to 0.5 and between 1 and 3.5. And I just here change this one, the lower bound of the parameter, the upper bound of the parameters. And here I have a kind of I have a kind of extra work. I have done a kind of extra work here because sometimes the optimal design is kind of symmetric around the points. So in logistic model, it is well known that the design is symmetric around this point. So it is 0 plus 3.5 divided by 2. And when you just set this one, you will reduce the number of dimension in the search space, and you will get the result more faster. So I did that, and this is the result again. So this is the design point. So I should tell the experimenter to choose this level with this weights. For example, if he has 500 people, he should, for example, just inject 0.34 milligrams, 0.34 milligrams to the persons with this weight. He should choose this persons based on this weight. And this is the plot, and this is the derivative plot again. So you will see that it is multimodal optimization. We always dealing with this kind of optimization here. And this is the standardized version. So again, I will just, it is for exponential model, and here the lower bound, the upper bound of the parameter and type is standardized. So I changed the cut to 3 because when I check it with 2, it was not optimal. So I just increase it to 3. And this is the result. And you see that the efficiency lower bound is very high. And this is the plot. And we can also have a model with 2 independent variables. So here the design interval or design space here. And it automatically plot, the package automatically plot for you the sensitivity, the derivative plots and the contour plot. And finally, it is optimum on the average design. So instead of a kind of initial values or a lower bound or upper bound for the parameter, I can have a set of values. They call it optimum on the average design or a kind of discrete Bayesian optimal design. And I can give weight to them. And then again, it is another function, but it is the same. It is with the same structure here. And finally, I will have the plot again here. Thank you very much.
We have time for a few questions. Yeah.
Yes, please.
The visual information matrix is a very low measure, and it depends on parameterization. So also the sigma values depend on parameterization. For example, if you are on a locked space with parameters and so on. So how robust is this approach with respect to different parameterization models?
Yeah, yes, you are right. For locally optimal design, we had this problem because you should check the robustness for I mean, with respect to each initial value. But for Bayesian optimal design, we say it is robust in average to this point in this interval or in this area. Or for minimax optimal design, we say our design protects us against the worst scenario that can happen, the maximum over the parameter space. This is the worst scenario. So it is, I mean, we just formulate it like that. No, not yet. Yeah. What minimum? I mean. Yes. No, I mean, it should be given by the user. Depends on the user. I mean, he should give it based on the research. I mean, you mean the lower bound and upper bound of the? No, it should be given by the user. I don't get the question because I mean we have a design inter.
Usually you have some practical reason.
Yes.
The lower and the mid.
Yes.
The rest could be something that you don't know where to put the optimal user response on.
No.
The lower and the minimum, obviously you want to have them.
I think because it is very flexible and you can put different model, I cannot set a default value for them. So it would be better if it will be given by the user.
Okay, thanks once more.
Thank you.